Hello viewers, we're taking you through the story of A-Level Physics Paper 2. And this video I'm going to go through the part of a meter bridge. So this part is under the topic of current electricity and is suitable for students, and this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we start, let's first look at the course outline of this paper. So physics paper 2 is divided into 4 parts. The first part is optics, where 2 questions come from these topics and a student must answer 1. Next part is physical optics, where 2 questions come from these topics and a student must answer 1. The third part is electrostatics and electricity, where 3 questions come from these topics, and the fourth one is magnetism and AC, where 3 questions come from these topics. So you can choose to answer 2 from here and 1 from here, or 1 from here and 2 from here, to make the 5 questions for a complete paper, from a complete paper. So we already covered electrostatics and capacitors. Now we are on current electricity. And current electricity, we have done the calculations of part 1, part 2, part 3, part 4, part 5, part 6, part 7, part 8. Now we are on part 9, which is meter bridge. So we are interested in calculations, but complete notes are available in the book Mastering A-Level Physics Paper 2, where clear notes, worked examples, and trial questions of all the topics are available. So in this video, we're interested in the worked examples found in this book, but the notes can be got by getting yourself a copy by contacting this author. A complete set of Physics Paper 1 has 3 books. One is Mastering A-Level Physics Paper 1, another one is Mastering A-Level Physics Paper 2, and Topical Question Bank. If you also do Principal Math, there is the set is 3 books. One is Mastering A-Level Mathematics Paper 1, Mathematics Paper 2, and the Topical Question Bank. If it is Subsidiary Math, it is only 1 book. And if it is O-Level Math, O-Level Physics, there is the 2 books, and also Math, O-Level Math, 1 book. So if you need yourself a copy, you can contact the author on any of these contacts. So we shall start our topic of a meter bridge. So the simple laboratory form of a Wheatstone bridge is what we call a meter bridge. And it consists of a uniform resistance wire AB, which is 1 meter long, connected in series with a driver circuit as shown below. So we need to illustrate how a meter bridge looks like. So this is how a meter bridge looks like. So these ones are metal plates. These ones, this is a metal plate, and this is also a metal plate. So that means that when you connect here and also here, it means that there is continuity, because this is a metal plate which is conducting. So this is the length uniform resistance wire AB. This is the uniform resistance wire, and it is 1 meter long, which is 100 centimeters. That means that if I get this length plus this length, I should be able to get 1 meter or 100 centimeters. Therefore, usually they will give you only one length, and for you to get the other length will be got by subtracting. You will say 100 minus R1 minus L1 to get L2, as you have seen the calculations. Then here, current flows when the switch is closed. Current will flow, and at this junction it will split. I1 will go through this, I2 will go through the resistance wire. So it is I1 which goes through this, let's say R1, and also R2, and I2 goes through this uniform resistance wire. And at this junction it combines to go back to the source. So this is what we call the left-hand gap, and this one we call it the right-hand gap. And R1 is called the resistance in the left-hand gap. R2 is called resistance in the right-hand gap. So the unknown resistance R1 and the known resistance R2 are connected respectively in the left-hand gap and right-hand gap of the bridge. Heavy brass or copper strips, SC, these ones, copper strips, this, and that, whose resistances are generally negligible, are used for the connection of the various parts of the bridge. So they provide continuity. So just like we saw balance condition in a Wheatstone bridge, even here we shall look at balance condition of a Metre bridge. So let's first redraw the diagram. So in under Wheatstone bridge, we got balance condition by adjusting the values of the resistances. But here for Metre bridge, we get balance condition by sliding the jockey along the slide wire. So this is a jockey, so it is moved along this wire until this galvanometer shows 0 deflection. When that point is reached, you stop and note that point. So in this case, it is point 2 where the galvanometer showed no deflection. So we stop at that point and we measure this length from A to 2 and also from 2 to B. So A to 2 will be L1 and 2 to B will be L2. So these distances are measured only when the galvanometer shows no deflection. So when it shows no deflection, it means that the current, when it reaches here, it is the same current which goes through, the current which goes through R1 is the same current which goes through R2. So just say, let's see how we can get the balance condition. So switch S is closed and jockey tapped at near end points on the wire such that it gives a two-way deflection. For example, this helps you to know whether you'll be able to get a balance point or not. So if you bring this jockey and tap it here and it deflects to the left, and then you bring it this side and put it near this end B and it deflects to the right, it implies that at a certain point it will show no deflection. But if you put it at end A, it deflects to the left, and also end B deflects more to the left, it implies that you can never get a balance condition or a balance point. So this one is used to test whether you will be able to get a balance point. After that is successful, then you can go ahead to get the balance point. How? So we shall get it by, so the jockey is tapped at different points of the wire. Notice what we are saying, tapped, until the galvanometer shows no deflection, and thus the current flowing through the galvanometer is 0. So balance point is got when the current through the galvanometer is 0, and in this case the meter bridge is said to be balanced. So in this case the balance point was at point 2. So after getting that point, what next? So at balance point, it implies that the potential at P is equal to potential at Q. Therefore, PD across R1 is equal to PD across HU. Let's just look at that. So just like we did for Wilson Bridge, the potential at this point, so this is our point P. If we go to put it there, you can put it there. Potential at P is equal to potential at Q, meaning that PD across R1 is equal to PD across HU. Similarly, PD across R2 is equal to PD across QB. So using that knowledge, you shall come up with this. Let I1 and I2 be the currents through R1 and HU respectively. Also let R be the resistance per unit length of wire AB. It implies that I1 R1, which is PD across R1, is equal to I2 small r L1. Why? Because this is the resistance. Remember, PD is IR. But how will you get the resistance of R2? It will be resistance per unit length multiplied by, or resistance per centimeter multiplied by the total length, which is L1. Also, since Ig is 0, it implies that I1 passes through R2 while I2 passes through tube B. Therefore, PD across R2 is equal to PD across tube B. PD across R2 is I1 R2 and PD across tube B is I2 R, which is resistance per centimeter times the total length. Now, when I divide equation 1 by equation 2, I'll come up with this. And from there, I realize that this I1 can cancel, I2 can cancel, R can cancel. So this should be small l. So in the end, I'll come up with R1 over R2 is equal to L1 over L2. So how is it connected in the diagram? In the diagram, what is here divided by what is here will be equal to this length divided by this length. So the order matters. This divided by this over this divided by this, or this divided by this divided by this divided by this. So equal to this divided by this. So you get the ratio of the resistances and the ratio of the lengths, balanced lengths, and equate the two. So now that we have seen the balance condition, next is to look at the questions. We already saw that. So question 1 came from UNEB 1996 part 2 question 10D and says, in the diagram above, the resistors P and Q are 5 ohm and 2 ohm respectively. So P is 5, Q is 2. A wire X of length 60 centimeters and diameter 0.02 millimeters is connected across P. So this is the wire. So that the balance point is 66.7 centimeters from A. So from here to here is 66.7. Calculate the resistivity of the wire. So combining the resistors X and P, because they're in parallel, we shall get product over sum. Then at balance, we shall come up with L1, which is that, and L2 will be got by saying 100 minus L1, which is that. Therefore, we shall get the ratio of the resistances over the ratio of the lengths. Let's see how it comes about. So what we do, we shall get this one divided by this equal to this length divided by this length. So when I substitute, I'll come up with that and make this the subject to come up with the resistance, combined resistance of X and P. But I already know that X combined resistance is equal to this, therefore I'll come and substitute. Then cross multiply and collect like terms, then make Rx the subject. So I've got the resistance of that wire X, but remember they want resistivity. So shall come and say that resistivity is equal to area, cross-section area, times resistance over length. So cross-section area is pi d squared over 4, where this d is the diameter. Therefore come and substitute, pi is there, diameter was in millimeters, that's why I multiply by 10 to the power negative 3 to convert it to meters. But it is squared, that's why I put a square here. Resistance, we have got it here, 4 is here, then the length was this, but it was centimeters, so we can multiply by 10 to the power negative 2 to make it meter. Then use a calculator to come up with the resistivity they want. So now we shall go to question 2, which came from UNEB 2016, paper 2, question 8C, and says, figure 4 shows two resistors P and Q of resistances 5 ohm and 2 ohm respectively, connected in two gaps of the meter bridge. This, a resistance X of cross-section area 1 millimeter squared is connected across P so that the balance point is 66.7 centimeters from A. So that means from A to C is 66.7. If the resistivity of wire X is this, and the length of wire AB of the meter bridge is 100 centimeters long, find the length of X. So let's first redraw and we put that wire X. So that means that this wire X and this resistance of P are in parallel. So the first thing to do is combine the two resistors in parallel to give you product over sum. Then at balance, this combined resistance over this will be equal to L1 over L2. So L1 will really, so it's that, meaning L2 will be this. So come and substitute to come up with that, substitute and make R1 the subject to give you this as the value of R1. So now that I have R1, I can get the value of X. To substitute for R1, cross multiply, collect like terms and make X the subject. Also, you know that resistance is equal to resistivity times length over cross-section area. Therefore, length will be resistance times cross-section area over resistivity. So resistance is that, cross-section area is that, and resistivity is that, to give you that as the length of wire X. Then question 3 came from UNEB 1995, paper 2, question 10b, Roman 3, and says, a resistance coil is connected across the left-hand gap of a meter bridge. When a 5 ohm standard resistor is connected across the right-hand gap of the meter bridge, and the coil is immersed in an ice-water mixture, the balance point is at a point 45 centimeters from the left hand end of the meter bridge. Okay. When the coil is immersed in a steam bath of 100 degrees Celsius, the balance point shifts to a point 52.8 centimeters from the left hand end of the bridge. Find the temperature coefficient of resistance of the material of the coil. So let's first make a sketch. Okay, so before heating, it was an ice water mixture and it was at 0 degrees Celsius, so this will be R0. Then when you heat to 100 degrees Celsius, this will be R100. So at 0 degrees Celsius, length was 45, then means L2 will be 100 minus 45, which gives that. Therefore, balance condition R0 over 5 is equal to L1 over L2. So we can substitute and make R0 not the subject. What about at 100 degrees Celsius? L1 will be that, L2 will be that. Therefore, at balance, we shall come and say R100 over that is equal to this over that. Then substitute and make R100 the subject. But we know that R theta is equal to R0 in brackets 1 plus alpha theta. Therefore, R100 will be R0 in brackets 1 plus 100 alpha. So substitute for R100 and R0, then be able to get the value of alpha. So alpha will be equal to this. And that will be the temperature coefficient of resistance they wanted. Then question 4 came from UNEB 217, paper 2, question 9C, Roman 1, and says, a standard resistor is connected across the right-hand gap of a meter bridge, and a coil X across the left-hand gap of the meter bridge. When coil X is heated to a temperature of 40 degrees Celsius, the balance length is this. Now it is in millimeters. From the left end of the meter bridge. When the temperature of X is raised to 100 degrees Celsius, the balance point is this, from the left end. Calculate the temperature coefficient of resistance of the coil X. So just still follow the same procedure. Let's first make a sketch. It will be the same sketch. Okay, so just say at 40 degrees Celsius, L1 was that, L2 will be got by, now we are using 1000 because 1 meter is equal to 1000 millimeters. So balance condition, substitute, and make R40 the subject. That is will be equation 1. Then for equation 2, that will be at 100. So L1 is that, L2 is that, then balance condition, substitute, and make R100 the subject. But we know that R theta is equal to R naught in brackets 1 plus alpha theta. Therefore, when I get the ratio, R100 is that, and also R40 is that. When I divide the two, I'll come up with this over this equal to this over that to give you this. Then I'll substitute equation 2, I'll substitute for R40 and R100 to give you that. So this was the R100 and R40. So R40 is the reciprocal because it was division, now it is multiplication. So when you change the sign, you get the reciprocal. Here it remains the same. So this RS cancels, and when you simplify the rest, you come up with this. Then here the R naught cancels. When I cross multiply, I come up with that, open brackets, come up with that, collect like terms, and make alpha the subject. And that's what they wanted. Then question 5 came from UNEB 2012, paper 2, question 8E, and says, in an experiment to investigate the variation of resistance with temperature, a nickel wire and a 10 ohm standard resistor were connected in the left hand gap and right hand gap respectively of the meter bridge. When the nickel wire is at 100 degrees Celsius, a balance point is 40 centimeters from the end of the meter bridge adjacent to the nickel wire. When the nickel wire is at 100 degrees Celsius, a balance point is 50 centimeters from the same end of the meter bridge. Calculate the temperature of the nickel wire if the balance length is 42 centimeters. So still we shall make the same sketch. Okay, so when it comes to a meter bridge, it's not a must to redraw this circuit diagram because it will take time. What we need, for me I'm drawing it to show you the balance condition. But if you have mastered the balance condition, then this diagram you don't need to draw it. So what you need to know is to master the balance condition and start from there. So if you mastered it, you could bypass the whole of this diagram and start by saying at 0 degrees, L1 is that, L2 is that, then quote the balance condition, substitute, and make R naught the subject. So this is what they want. They don't need this diagram. I'm just redrawing it to show you how this balance condition comes about. But when you have grasped the concept, endeavor not to draw this because it will consume a lot of time, yet time will never be there in an exam. So that is R naught. What about at 100 degrees Celsius? L1 is that, L2 is that, balance condition, substitute, and make R100 the subject. But you know that R theta is equal to this, therefore R100 is that. So substitute for R100 and R0, and you'll be able to look for a way of making alpha the subject. And that's what they wanted. So if the balanced length is this, it implies that that is that, and also that is that. Therefore, balanced condition is that, and substitute, then get the value of r of theta. Remember, they want the temperature of the nickel wire. So they want the temperature of the nickel wire. So you have got the temperature coefficient of resistance and also the resistance at that unknown temperature. Therefore, you can easily get the temperature of the nickel wire. So we shall come and substitute for r theta, r0, alpha, and remain with theta, which is the only unknown. So look for getting the value of theta. So theta will be equal to that. So we shall use, it's advisable to use 2 decimal points. So here you should round off to 2 decimal points. So now we shall go to another term, still under balanced condition of a meter bridge. There's a term called end errors or end connections in a meter bridge. So what are these end errors? So when the length being measured is very small, the effect of end errors due to imperfect soldering becomes comparable to the resistance of the connecting wires. That means that the error in the measured value becomes significant. So due to imperfect contacts at the ends A and B of the meter bridge, extra resistances equivalent to lengths LA and LB of the wire at A and B respectively are introduced in the wire. So because of this imperfect soldering, there will be an extra resistance due to this length LA and LB at the ends of the wires. And that resistance will not be negligible, because if we have said that if the length is being measured is very small, the effect of end errors is significant. So in the previous questions we have been ignoring the end errors because they were negligible, but there are cases when these end errors are not negligible. In that case, you shouldn't neglect them. So these extra lengths are called end errors or end connections, and they should never be ignored in some cases where this length being measured is small. So how can you determine these end errors? So in order to determine the end errors, the resistances R1 and R2 are placed in the left and right hand gaps respectively, and the balanced lengths L1 and L2 measured and recorded. So the resistances are then interchanged such that the resistance R1 is placed in the right hand gap while R2 is placed in the left hand gap. The new balanced lengths L1 prime and L2 prime are also obtained. So before interchanging the resistances at balance, it implies that R1 over R2 is equal to L1 plus LA over L2 plus LB. Now this LA and LB are what we call the end errors. So this LA is the end error at A, and this is end error at B. So they are constant, meaning that even after interchanging, they will still have, the values will be the same, LA and LB. Therefore, after interchanging, still shall follow the same procedure. R2 over R1 is equal to L1 prime plus LA over L2 prime plus LB. So now we have two equations and two unknowns, meaning we can solve them simultaneously. So basically that is how they get the end errors. But to understand it well, let's go through this question. So question 6 came from UNEB, March 1998, part 2, question 8a, Roman 3, and it says, when resistors of resistances 8 ohm, 4 ohm and 8 ohm are connected respectively in the left and right hand gaps of the meter bridge, a balance point is obtained at a point at distance 32 centimeters from the left end of the meter bridge. On interchanging the resistors, a balance point is obtained at a point 68 centimeters from the left hand end. The resistance of the uniform wire of the meter bridge is 5 ohm. Calculate the end errors. So let LA and LB be the end errors. Before interchanging, let's just get a sketch diagram for you to understand this. Okay, so like I said, when it comes to meter bridge circuit questions, it is not a must to redraw the circuit because it takes a lot of time. I'm just drawing it to make you understand the concept of, when you master the concept of balance point, of what happens at balance, then you don't need to draw the circuit. So this is R1, this is now R2, this is length L1, L2 can be got by subtracting. Therefore, at balance before interchange, we shall come up with, we have R1 that, R2 is that, L1 is that, and L2 is that. So this is supposed to be 32. This is 32. Therefore, it means that R1 over R2 is equal to L1 plus LB over L2 plus LB. Then substitute, cross multiply, simplify, and then rearrange to get that, to make LB the subject. So that is before interchanging. What about after interchanging? So after interchanging, we have R3 that, R4 that, and L3 that, L4 that. Therefore, at balance, that's what happens. Then substitute, cross multiply, reduce, and substitute. So here, what we have done, we have substituted for LB to give you this, so that we have only one unknown. So our aim is to look for making LA the subject, and that will be the value of LA. When we get LA, we can be able to get LB, and that will be the value of LB. So those are the end error lengths. What about the resistances? So resistance per meter is our total resistance of AB divided by 100 to give you this. That means that the end error resistance at A, at side A, is this. So R0, which is the resistance per centimeter, times the total length, which gives that. What about the end error resistance at B? To B, resistance per centimeter times the length, which gives you that. And that's what they wanted. So that brings us to the end of this video. Thank you for watching, and bear in mind the next video will now be on potentiometers. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.